There's also not just the asteroid belt, which is in here. There's other asteroids as well. You can see there's a group here called the Trojans. There's the Greeks over here. And then these orangey ones are in 3 sort of locations around here called the Hildas. So the asteroid belt isn't just what most people think of, this big, massive asteroids that are travelling around the Sun between Mars and Jupiter, but there's actually other groups as well. The Trojans and the Greeks are actually in a particular spot. You would have noticed they're sort of the same distance as what Jupiter is. We've got the Trojans which lag behind and the Greeks go ahead. And they sit at 2 particular points in the orbit where the gravity from Jupiter and the gravity from the Sun sort of cancels one another. And that's at an angle of 60 degrees before and after Jupiter's orbit. The gravity there is sort of neutralised by the Sun and Jupiter, and these asteroids can stay there for a long time. And Jupiter doesn't speed them up or slow them down, they're just sort of stuck in limbo and they continue to orbit the Sun in quite a stable orbit. There's about 4,000 that they know of now. Possibly as many as 1 million bigger than a kilometre across. So there's almost as many asteroids in these 2 groups as what there is in the asteroid belt, which is quite a bit further in. So these are captured by Jupiter and they stay in that orbit and they could be there for many, many millions or billions of years. Then we had the Hildas. Now the Hildas don't actually travel in a triangular orbit like that. This is just a snapshot of what they look like. They all have their own orbits, but if you were to take a picture of them at any instant, they tend to join together at particular locations. And if we were to look at the other one before, you'll see this is about 30 degrees before, 30 degrees after, and that's on the opposite side to Jupiter. Again, because of the gravitational effect of Jupiter, it keeps them in these locations all the time, and it's stable. They can stay there for a very long time. They have what they call a resonance. So every time they go around the Sun twice, Jupiter goes around 3 times. So if they start to drift out a little bit, one of the orbits will come around and Jupiter will line up with them and the gravity will pull them back into line. And then they'll go around the Sun 2 more times, or 3 more times, and Jupiter will come around its second time and it'll line up and it will pull it back into line again. So they stay in this orbit all the time because Jupiter is constantly coming back, pulling them back into orbit every 2 Jupiter orbits, which is about every 22, 24 years, something like that. So they get a little tug and they stay there. We have the Centaurs. The Centaurs is another whole group of asteroids again. And what's so special about these, you'll see they don't go inside Jupiter's orbit, but they do go out as far as Uranus and Neptune, and there's whole masses of these as well. So they don't cross the path of the inner planets, so they're not going to hit us. And they think there's about maybe 40,000 of these ones bigger than a kilometre. But because they cross the path of the bigger planets at some time, like Saturn or Neptune or something, can pull on them so hard that it pulls them out of their orbit and they can be sent into the Sun or into the Earth or whatever. So they'll only stay in these orbits for perhaps a few million years at most, and then something will pull on them or they'll smash into a planet and they'll change their orbit again. So it's not stable for very long. This is a whole nother group of asteroids. Another one called NEOs, or near-Earth objects. If we look at something like this, you'll see it actually could get quite close. As the Earth goes around here, if it happens to come down to here, we might be in trouble, but most of them actually orbit above the Earth. So if the Earth is going around here, they're actually going like this. So they do get closer to the Sun than we do, but because they're at this steep angle, they won't hit us. They just happen to get closer to the Earth than what we do. But we're not in any real danger of getting hit. There's about 8,000 of these out there as well, floating around in space. There's about 150 that are bigger than a kilometre that actually cross the Earth's orbit. So the Earth goes around here, and they follow the same path. They cross it at some time. So there is a possibility that there could be 150 rocks out there as big as a small suburb heading our way at some time. One of them actually did come close back in June 2004, one called Apophis. It actually came very, very close to the Earth, but they determined that it wasn't going to hit us. But as it went past, they calculated it was going to come back to the Earth again in about 2029. And there was a very real possibility at the time that it was going to hit us. But after they did some more measurements, they checked the orbit of it, they've discovered that it's only got a very small percentage chance of hitting the Earth. But when it does come back in 2029, it will come so close to the Earth that it will actually be below the satellites. So one risk is that it may hit some of our satellites up there, and it will be visible to the naked eye. It'll be about magnitude 3, so if you look at the Southern Cross, a little bit dimmer than the dimmest star on the Southern Cross. And you'll see that star move. With the naked eye, it'll be noticeable. You will see it gradually move across the sky. And I'm sure in 2029 it'll be in all the newspapers. So you won't have to worry about missing it, because providing it's not a night like tonight, everyone will be out there with their telescopes to watch this rock go past. Fortunately, if they have got it wrong, these are the most likely places it will hit. Right? It is more likely to hit Russia or the Pacific, or right through Central America and maybe the coast of Africa. There's virtually no chance whatsoever it will hit Australia. But if they've got it wrong, it may, most likely it would land in the Pacific, because that's the largest area. But even if it was to hit a city, it would perhaps demolish a city, but that's about all. So if it was to hit Melbourne, that would be the end of Melbourne, and there'd be a big fire and a lot of mess, but that would be all. It's not big enough to do anything much. It's only a few hundred feet across. Now, some rocks, of course, do hit the Earth. And this is one in Arizona. The one that made this hole is quite a bit smaller than Apophis, though. Right, the one that made this was about 20 or 30 metres across. Apophis is maybe 10 times bigger. So it would be a much bigger hole in the ground. But this is one in Arizona. It's about 1.2 kilometres across, and it was solid iron. And this is a little piece of it. That's a little fragment of the meteorite that made that hole in the ground. So they do hit the ground and they do make holes. There was another one about between 4,000 and 6,000 years ago, landed in northern Argentina. It was in an area called Campo del Cielo, which is Spanish for field of the heavens or field of the skies. When this meteorite came in, it actually broke up, and there's 22 craters in this area where pieces of this meteorite have landed. They've picked up about 100 tonnes of this material so far. You can see how big some of the pieces are. The biggest one's bigger than this, about the size of a Volkswagen is the biggest piece they've got. And I've got my bit. This is mine. He weighs about 11 kilos. And here's a piece of that meteorite that landed in Argentina, and I call him Aussie. And hopefully you can see why I call him Aussie. It just happens to look like Australia, but it's just a piece of meteorite. It's just a piece of iron from space that just happens to look a lot like Australia. So if you pick that up later, you will need both hands, because it looks deceivingly light. When you pick it up, it's much, much heavier than you think. So that's enough of all the little rocks. Let's go on to some of the bigger things. Now, when they discovered Uranus, and that was back in 1781, they measured its orbit, and it didn't seem to follow the orbit they expected. It was actually travelling faster than what they thought it would. So they speculated that if there was another planet out there whose gravity was pulling on it, that would answer the question as to why Uranus was going faster than expected, that there was another planet out there whose gravity was tugging it along. So after a lot of calculations, they calculate approximately where this planet would need to be to have this effect. And they turned a telescope there, and they found Neptune. That was the first planet they've ever found by mathematics. They calculated where it would be. They calculated the position to within about twice the diameter of the moon. So they were within 2 moon diameters of where it should be, which is not bad considering how many moon diameters there is in the whole sky. And this was done in the mid-1800s. They had no calculator. All the calculations were done with pen and paper. And then they discovered, after they found Neptune, that Neptune's orbit wasn't proceeding as they expected. It also was behaving a little bit different to what they thought it would be, where it should be. There was something, they thought there's something else out there. Maybe there's another planet, and that's pulling on Neptune, and that's making Neptune go funny. So then they started the hunt for what they call Planet X, the unknown. And they searched for ages for this. Until 1930, they discovered the next planet. This was found by Clyde Tombaugh, who died not that long ago now, about 14 years ago. And he found that what he needed to do to find this planet, fortunately they had photography by then, and he would take all these pictures of the sky, and then a few days later take identical exposures of the same area, and then he would look at these pictures with masses of stars and go, did one move? He did this for about 2 million stars, using what they call a blink comparator microscope, which has the 2 images and it basically flips between each one. And if something moves, the eye will see all the other stars stay there, and the one that moves will go from there to there, and you'll notice it. Now, without that arrow, can you see which one moved? Even with the arrow, it's very hard to see, but this little dot here, which is about here, isn't there. There's a new dot just over here. You can see these 2 dots up here, those 2 dots are still there, but there isn't one there. And that's what he looked at, and that's how he discovered Pluto. That one little dot had moved. It took him many, many years, and I'm sure with absolutely splitting headaches by the end of the day, I can imagine. Now, after they discovered it, of course, the first thing they had to do was give it a name. So they had this competition of what to call this new planet. And it was won by an 11-year-old girl called Venetia Burney. She put forward the name Pluto. Pluto was the god of the underworld, because she figured that little Pluto is so far out in space it must be freezing cold, that the god of the underworld would be a very suitable name. So she was awarded a prize of £5 for that answer. £5 is about $10, but $10 back then is probably worth maybe $500 or $600 in today's terms. So it mightn't seem like much, but to an 11-year-old, a $500 prize is probably pretty good.